well, after I started uploading one video, so it's working now. Okay, so we're looking at 59 on page 334. Okay, so 55,000 max attendance. Ticket price is at 10. Average attendance 27,000. Ticket price is lowered to 8. Then the attendance 33,000. Find the demand function assuming that it is linear. So how do we determine the demand function and what will it equal to? So when we talk about the demand, we have basically a product. So the demand is a product of what? So we have here, do you remember, we have not done this in this class. Do you remember the demand and supply situation? So there are two functions. The higher the price, the lower the demand, correct? Okay, so the demand function is a decreasing function based on price. What about, since I just mentioned supply, what about the supply? They would love to sell at the highest possible price. And basically, this is the equilibrium point. Equilibrium point. Right? Where everybody's happy. We're happy with the price, and they're happy to sell. So D of P. So the demand function depends on price, and it has a negative slope. So we're told that at 10, 27,000, when the price is 10, 27,000 are attending. So this is 1 point. And when 8 are attending, when the price drops to 8, 33,000 So we are also told that this function is linear. So find the demand function assuming that it is linear. Okay. Let's find the slope. So 33,000 minus 27,000 divided by 8 minus 10. Because we are told it's linear, as we expect. So the numerator is 6,000. And the denominator is -2, so it's -3,000. It doesn't mean anything without the measurement unit. So what does this mean? And remember, it has two measurement units, one coming from the top and one coming from the denominator of this ratio. So it's -3,000 per dollar, right? For each dollar we increase the price, the attendance drops by 3,000. So it's spectators or attendance, it should be spectators, per dollar. Every dollar increase makes the attendance drop by 3,000 people. So if we go from $10 a ticket to 11, then the attendance will drop from 27 to 24. Okay. Yeah, but we haven't finished. Yes, of course. Yes. Yes. Yes, of course. We will. Yes. We'll choose a function. We'll create a function that has a slant asymptote in a minute. So find the demand function, assuming that it is linear. How should ticket prices be set to maximize revenue? Okay, that's a different story, right? How do I determine the revenue? So the revenue is R of X or R of price or a combo. So let's discuss that. So the revenue is price multiplied by number of tickets sold. That's our revenue. So what would you say the revenue would be for $10? It would be 27 times 10. What would be the revenue for 8? It would be 33,000 times 8. So 27,000 times 10 is the revenue if the ticket price is 10, and the 33,000 times 8 will be when it's 8. Okay. So the next step would be to identify a function here, because we need to maximize it. It says one more time, find how should the ticket prices be set? In other words, find P for max revenue. This is our question. Find what the price should be. Tell the manager of the baseball stadium, listen, if you set the price at blah, your revenues, your revenue from the sales of the tickets will be maximum. Okay, so then I'm going to call, it doesn't matter, let's call it P. So from the price of, so they're giving us $10, right? So 10 for 27,000 and 27,000 attendance and 8 for 33,000. Okay. So if we increase the price by $1, then 55,000 minus 3,000. If I have P plus $2, then I get 55,000 minus twice 3,000. If I decrease now the price, and if I have P, then I have times 55,000. If I have P minus 1, then I have 55,000 plus 3,000. If I have P minus 2, then I have 55,000 plus twice 3,000. This is the main idea. We haven't gotten to a function just yet. So we have to express this as one function, of course. But this is the idea. If I increase the price, the number of attendees drops by 3,000. If I increase by $2, the number of the capacity minus 2 times 3,000. If I keep P, then it's 55,000, which will be the maximum. P minus 1, then 55,000 plus 3,000, but I can't really do that because I don't have a capacity. The capacity is, I just wanted to show you the idea. So the capacity is 55,000 maximum. So then I think we're close to writing a function. So R of X will be $10 minus X times 55,000 minus 3,000x. Let's think about each and every step. Let's check if that's true. We are decreasing the price. We are increasing the price. We are decreasing the number of attendees. Okay, one more time. So the price for $10, if we increase the price, we decrease the number of, so if we increase the price by 1, we decrease the number of attendees by 3,000. If we increase the price by 2, we decrease the number of attendees by 6,000. If we increase the price by 3, then 3,000 times 3 subtracted from 55,000. Ready? Okay. Now we are going to distribute, and we are going to differentiate. We're going to set equal to 0, and then we're going to come up with the price that the stadium should charge in order to get the maximum profit. Okay, so R of x. In other words, what do they should do here? What should x be? Okay, so 550,000 plus 55,000x minus 30,000x, minus 30,000x squared. Okay, let's see what happens next. We combine like terms. And in descending order, negative 3,000x squared and plus, I think it's 25,000x and plus 550,000. I differentiate and get negative 6,000x plus this. I set r prime equal to 0, and I get 25 divided by 6. Dollars, of course. To be added to 10. Okay, I haven't shown that this is giving us a maximum. Of course it is, because it's quadratic and it has a maximum. But I still have to show this. But we haven't found the final answer just yet. So I have r prime, 0, 25 over 6 is 0. I study the sign. Obviously it's positive, and this is negative. So this gives us a maximum. Okay, so however, the price is this, not just x alone. This is the price times the number of attendees for a maximum profit. Okay, so price is 10 plus 25 divided by 6. So this is the price that they should, I just want to plug it in to determine the maximum revenue also. So they should charge $14.17. Okay, so now we want to find the maximum revenue. So go back to the function. Here it is. 10, so 14.17. So I have 10 plus, I don't want to calculate like that. I just want to have exact, if I can get a better revenue. So 55,000 minus 3,000 times x times x, which is 25 over 6. Okay. Say it again. So I have not determined r yet. I'm calculating this right now. But x is 25 over 6, which is this piece, which is also this piece. Better? Okay. So I can simplify, because this is 5,000. So then 55,000 minus. Oh yeah, of course. Yeah, I said, how can I get a negative number? That's a good advice I'm giving them, to be in the minus. Okay, so 55,000. It is 500, yes. Okay, so minus 500 times 25. It's 42, okay, and then multiplied by 10 plus. Okay, so I got 602,083.33. Guaranteed to give us the maximum. So, as you see, $10 times 55,000 will not give a maximum. So increasing the price by $4.17 is the best deal that they can get. By increasing it by $4.17, they will decrease the attendance. They will not get a full stadium, 55,000, but they will definitely obtain the maximum possible profit they can get, which is 602,083.33. We're not asked to determine that. We're only asked to determine what would be the maximum, what would be the price for a maximum revenue. Interesting. Good. We wanted to look at slant asymptote. Very good. Can anyone give us a function, rational function, of course, that would have a slant asymptote? Okay, negative 3x cubed plus 2x plus 9 over x squared plus 1. I'm going to erase the 2 because we're going to have fractions. Okay, will this function have a slant asymptote, by the way?
Yes.
How come?
That's how great it is.
Exactly. So if the ratio is aligned, that's the whole deal. The ratio is aligned because when I divide degree 3 by degree 2, I get a line. If I divide degree 4 by degree 2, I do not get a line, so that cannot be a slant asymptote. So I see that there is a missing term. The degree is 3. But there is a missing term, and I may need to use that spot. If not, that's fine. It's not going to hurt if it's there. But if I need it and it's not there, I'll have difficulties. So x squared times what is negative 3x squared? And we have negative 3. And then we distribute negative 3x squared, but we have to change the sign. And oh, thank you, of course. I just said it. Thank you very much. Sorry about that. So negative 3x times x squared is negative 3x cubed. Change the sign. Negative 3x times 1 is negative 3x. Change the sign. Bring down the next in line, which is 5x plus 9. And I have to stop because x squared does not go into 5x. So the answer is negative 3x and plus 5x plus 9 over x squared plus 1. Let's say you have doubts about this. Maybe you don't remember, or you just have a minute and you want to check. How will you check? You will multiply this by this and add this, right? So negative 3x times x squared plus 1 plus 5x plus 9. I have to recover this. If I don't, then the answer is incorrect. So I distribute first, negative 3x cubed minus 3x plus 5x plus 9, and I get negative 3x squared plus 2x plus 9, and that's exactly what I started with. Therefore, the correct answer is indeed negative 3x plus 5x plus 9. Perfect. Anything else that you can think of from test 2? From test 3? The mean value theorem, yes. Here it is. Let's look at another mean value theorem. This is section 4.2. Let's say problem 9 on page 289. We are given f of x, which is 2x squared minus 3x plus 1, and the interval is 0, 2. And we're asked, verify the hypothesis. I have to write that, number one, f is continuous on 0, 2 as a Pauli function, which we know is continuous everywhere. I have to write number 2, that is differentiable. F is differentiable on the open interval 0, 2. What does that mean? We don't care if it's differentiable at the endpoints. We really don't. That's not the point. Okay, so therefore, there exists a C in the open interval 0, 2 such that f prime of C equals f of B minus f of A over B minus A, where A is 0, B is 2. So I have to find f of 0, which is 1, and I have to find f of 2, which is 4 times 2 is 8, 8 minus 6 plus 1, I got 3. I have to find f prime of x, which is 4x minus 3. And now I'm ready to write this equation. F prime of c will be 4c minus 3 equals 3 minus 1 over 2 minus 0. So 4c minus 3 equals 2 over 2, which is 1. Very nice. 4c equals 4, c equals 1. And 1 has to be in the interval 0, 2. It is, because it's guaranteed by the mean value theorem. Okay, so let's go back to test 2 and see what we should review from test 2, or whatever you want. Here's test 2. So we had differentiation rules. I'm losing my voice. We have differentiation rules, all sorts. We had differentiation of a function ratio. Yes, Matt?
Implicit differentiation.
Yes, yes. You want this or implicit differentiation, because it's a combo. So there was, we didn't have an exact implicit differentiation. We can choose. Let's choose. Let's start with that. So implicit differentiation is in section 3.4 or 3.5. Let's take a look. Product chain rule 3.4, implicit differentiation. Chain rule 3.4, yes, implicit differentiation in 3.5. It doesn't have to be from these, it can be from these, whatever you want to choose.
Number 13.
Number 13, very good. '13 on page 215. 13. 4 cosine x sine y equals 1. We are asked to find dy over dx, which means that we know that x is an independent variable, but y is not a variable. Y is a function of x. So we'll start by differentiating both sides. The right-hand side will be 0, but the left-hand side will be a product. So 4, leave the 4 outside. There is no need to involve 4 in any of our calculations. You can wait patiently and then we'll distribute it. Cosine prime is cosine x, so cosine prime will be negative sine x. And we multiply by sine y, and then plus cosine x, and because it's the product rule. So now we have to differentiate sine y. And when I differentiate sine, I get cosine. But since y is a function of x, I have to multiply by dy over dx. Is this okay so far? We haven't finished. So we have a product of cosine and sine. I differentiate cosine, I get this, and I have to copy sine. Plus, I copy the first function, and I differentiate the second one, but when I differentiate sine y, I get cosine y times dy over dx. Okay, now I can even divide by 4. I don't even care for it. So I have then negative sine x sine y. I will move this term to the other side. Negative cosine x cosine y dy over dx. Look how nice this is. So we divide by this, and we get dy over dx, which is tangent x tangent y. Very nice. Good pick, Matt. Well done. Questions? Which one? Oh, I can divide both sides by 4. Even if we have it in there, it will go away. It will be still 1. Good. Next question. Let's go back. Remember, something like this cannot be differentiated without applying log to both sides. We don't have a formula for a function raised to another function. Yes. That's why we need to review certain things more than once. That's why, okay, here they are, right here. All these from 43 to 50. Which one? 46 it is. Forty-six. I see. So 46 on page 223. y equals the square root of x, everything raised to the x. So again, we cannot simply differentiate this. We have to apply natural log to both sides and then differentiate. So natural log y equals x times natural log the square root of x. Is this okay? What I recommend is apply a property, which means the natural log of the square root of x is 1/2 natural log x. So natural log y will be x over 2 natural log x. Or, even better, 1 over 2 times x natural log x. You know I don't like involving these constants. They are factors, they can wait. It's not a big deal. But if I keep them in the problem, they make the calculations potentially more difficult, potentially. Okay, only now I'm ready to differentiate. So the left-hand side is 1 over y, but dy over dx. Remember, y is a function of x, and x is the independent variable. Keep 1/2 outside, can wait patiently. And now we differentiate the inside as a product. X prime is 1 times natural log x plus x times natural log x prime, which is so much better than having to differentiate the square root. You get the same answer, of course. So then dy over dx, remember I have to multiply by y is the square root of x raised to the x power over 2. And then in parentheses, I have natural log x plus 1. And there is nothing else I need to do here.
You know how you
Yes?
find the second derivative or something like that?
Say again?
You know how like you do like the second derivative or something like that? So you plug in dy over dx into the next equation and then you continue.
When you try with the second derivative,
I'm like implicit differentiation, like you plug in dy over dx into the next equation and then you continue. I don't know what problem it is. I know it was not. Because I know like the next step you plug in dy over dx into it and then you continue.
when can I remember that? When did we do that? When we found the second derivative and then we plugged it in?
No.
I'm not saying it's not, I just don't remember what the...
I just want the next step you plug in. You put in dy over dx into the next step and then you continue.
Was there a particular problem?
Yeah, it had to do with the second derivative of it. Yeah, it was like, that's what, yeah, it was implicit differentiation with the second derivative.
There's probably a website out there.
Pretty sure.
Oh, so you're asked to find the second derivative.
Yes, that's what it
Yeah.
was.
Oh, okay. So I'm sure there is a problem here with implicit differentiation, right?
Then you took the first derivative, substitute that.
Yeah.
This one? So let's choose one and find the second derivative by differentiating implicitly.
Could you just stick to 35?
35? Very good. That's the ellipse, an ellipse. So 9x squared 9x squared plus y squared equals 9. Very good. So we want to find the first derivative. In other words, dy over dx first. So then we have 18x plus 2y dy over dx equals 0. So one option would be to solve for dy over dx first. That's one option. Will be negative 18x over 2y. Or dy over dx equals negative 9x over y. And now, in order to find the second derivative, I will differentiate again. The left-hand side is just the second derivative, nothing else. So d2y over dx2, negative 9 is negative 9, but now I have to be careful. Top prime is 1 times y minus top times the denominator prime, which is dy over dx. I will separate the fraction right now. d2y over dx2 is negative 9y over y squared. Negative 9 times negative x over y squared. And yes, and now I have to replace this by that, by this. So d2y over dx2, negative 9 over y plus 9x over y squared times negative 18x over 2y. And I have to simplify it as much as I can, if any. Negative 9 over y minus x over 2y cubed. Is this what we wanted?